So in the last class, we started talking about the types, the different kind of tests that we have, right? The different types of areas where testing is required. And in one case, we saw that. So we started talking about the single mean test, right? And we saw that one very important application is of the single mean test is in assessing the causality in regression models. So basically, if I want to know whether y is explained by x or if the variations in y is explained by the variations in x, then this is the test that we should do, right? We should do the single mean test, and say our test hypothesis is beta equals to 0 versus the alternate hypothesis beta not equal to 0. So this is what we have done, right? So the beta equal to 0 is the null hypothesis, and the entire idea of the null hypothesis is to ensure that, or is to check whether, is to check on the fact that uh, that beta is equal to 0, in the sense, that that beta equal to 0 means that whatever causality I can observe between x and y, that's an observed causality. I do not have a kind of, what should I say, so I do not have uh, a significant causality involved into it, right? So this is something that I do not have. Therefore, so that is one of the parts that we had talked about. Now, today we will explore other different kind of tests, and we'll check where does the applicability lie. So now, so since we have stated, right, that this single mean difference test is used test for the causality, right? So how do we identify this? So, or what are the areas where this is used in risk? So where are the what are the places where we do this test? Let's say, for example, right, I have a very simple model. So I'm talking about a very simple, say, PD model, or I'm talking about a simple LGD model and stuff like that. So what I want to understand is that what are the factors, right, which the probability of a default probability of a borrower to default would depend. So basically, what happens is, so you know that for a probability of default model, our dependent variable is something like this. So for a PD model, in a PD model, what are we trying to understand? What we are trying to understand in a PD model is what exactly is the probability of a borrower to default in the next 12 months. Over here, what we have is y equals to 1. If the borrower defaults. In the next 12 months. In the next 12 months. So y equals to 1 if the borrower defaults in the next 12 months. The next part that we have over here is equal to 0. Okay. So now over here, our objective is to estimate the probability of default. Right. Now observe that when I talk about the probability of default, so what it means is that there is probability y equals to 1. Now this probability y equals to 1 is a fractional value, right? So this belongs to the interval 0 to 1, right? So over here, now observe that how is it that this behavior gets worked out with. So basically what I have over here is a probability y equals to 1, right, which belongs to 0 comma 1 and so on. So over here what we need to understand is the following, that so the dependent variable is the probability of default. Now this dependent variable follows the interval 0 comma 1, or it lies in the fractional set of values. Now the question that comes out over here is that the values that we have, or the variables with which we predict these values, right? So those variables are continuous in nature. So what happens is that when we are trying to, when we are trying to talk about, when we are trying to develop a probability of default model, the dependent variable is fractional in nature, right? But the independent variables are continuous in nature, right? So there is an inconsistency in the mapping, right? Because I cannot always write, say, I try to frame the model like this. I say that okay, probability y equals to 1 is a dependent variable, right? So that is equal to some parameter, some intercept beta 0 plus, say, beta 1 into the loan amount, so the amount of loan that has been given, the loan amount. So higher the loan amount, higher is the probability of default. Now observe one thing, that loan amount is a the loan amount over here is a continuous variable, but the dependent variable, which is the probability of default, that is a variable which lies in the fractional set, right? So over here what we need to do is we need to frame an understanding of uh, these three values, right? So over here what we have is beta 0 plus beta 1 loan underscore amount. So over here there is a inconsistency in the range of the variables. So why at one end what happens is we get to see that beta 1, so the loan amount is continuous. On the other hand, the variable that I'm trying to estimate is fractional in nature. And I cannot ensure that this sum product, so this part will always lie between 0 and 1. So because we cannot ensure that this will lie between 0 and 1, there is an inconsistency. Hence, if I have to use a regression model to estimate the dependent variable, then the first thing that I need to do is I need to convert this fractional variable into a continuous dependent variable. So this is something which is really very important at this stage. And after that, after we have done the conversion and all, then what we'll do is we will try to work with the correct. So over here, so this is how we are trying to, or this is how we try to work with. So now let us think about this one. So the first question that comes out over here is that how is it that I can convert this model into, from a continuous variable, how is it that I can convert it to a variable? So what we do is we convert this into the odds. So So the odds is nothing but the probability of y equals to 1 relative to the probability of y equal to 0. Right. So if you have a look into this, the probability y equals to 1 by the probability y equal to 0 is a continuous value. It's a positive continuous value. Now, to convert it into a totally continuous value, which will take both positive and negative value, what we do is we take the log of odds. So on the over here, this dependent variable is converted into the log of odds, in the log odds. So this log of odds is a continuous variable which takes any value from minus infinity to plus infinity. The reason is, say if the probability of y equals to 1 is lower than the probability of y equals to 0. So what I have over here is the probability y equals to 1 is less than the probability of y equal to 0. Then the probability of y equals to 1 by probability y equal to 0 is a fractional number. That is, it is a number which is less than 1, right? And if it is a value which is less than 1, then what I have is that this ratio will be less than equal to 1. Clear? So given that this is the criteria, right? So given that this is or this happens to be the idea, therefore what we have is probability y equals to 1. So therefore, whenever this ratio is less than equal to 1, the log of this value is always negative. So log of a fraction is always negative, and log of a positive value is also is positive. So therefore, what we have over here is the log of odds. Now, this log of odds is estimated using the independent variables. Now, when I'm trying to estimate the log of odds using the independent variables, what happens over here is I that is where I need to test. I need to know that does loan amount impact the log of odds of an outcome. So the does or would loan amount actually impact the chances of the borrower to be a good borrower or the chances of the borrower to be a defaulter. So is loan amount a very significant predictor of log of odds? Right. So in order to do that, what we do is we test whether the beta one is statistically significant or not. So the null hypothesis over here is beta one is equal to 0 versus the alternate hypothesis beta one not equal to. Right, so what we have over here is H0 is beta 1 equal to 0 versus the alternate hypothesis beta 1 not equal to 0. Right, great. So, in order to assess the causality of the variable, what we use is we use this particular test, use the single mean difference, the single mean test, right? So after this, the next thing that we talk about would be the mean difference test. So over here, over here we would be interested. We would like to talk about like what exactly is the mean difference test all about. So like what is the mean difference test? Why is it important for us to have the mean difference test and so on? Okay. So the next part that we bring over here is the mean difference test.
Hello.
Hi.
Yes, we can continue now.
Okay, great. Okay, so as I was saying, um, the mean difference test. Now, the mean difference test is designed to help us understand whether there exists a significant difference between the average of the two groups or not, between the mean of two groups or not. Now, say, so basically, what is the case over here, right? Say, basically, we assume that there are two groups over here or two sets of values. Right. So one is x1. And mu sigma square. So basically, what we say is that there is this mean mu, right? So basically, x1 follows a normal distribution with a mean mu and a variance sigma square. Or let's call it mu1 and variance sigma 1 square. Similarly, over here, what happens is x2 follows normal distribution with mean mu sigma 2 square. Okay. So over here what we have is that x1 follows normal distribution and x2 also follows a normal distribution. So I have two groups which are normally distributed. So this is one of the important characteristics of of mean difference test, where you start by checking for the test of normality. So what you do is you start by identifying normality among the variables. Right. So over here, what we have is a clear test of normality. So over here, so this is one of the most important characteristics for these t-tests, that they are very strongly based under the assumption of normality. And that is why these tests are known as parametric tests, because they start on the premise that the variables required for this test, so the rules that the observable required for this test must satisfy a certain criteria, which is test normality. Right, so it starts on the very premise, on the very same premise, that if you have, or if you are trying to perform this test, your variables must be following kind of a normal distribution. Now, after we have done this, right, so the next thing that we need to look into is again the following. That so what is this test all about? So before we move into the risk-based examples, right, of the application of this test in risk, let us just think about a very basic example. Right. Say consider that there are two brands, right? Say let's take Pizza Hut and Domino's, right? These are the two big brands, as we may say, for pizza. Right. Now both of them have outlets close to each other. Say both of them are based out of a mall, right? Say both of these have their operations in Cyber Hub, Gurgaon. Now what will happen is, now what Pizza Hut sees is that they provide a very superior quality product compared to what Domino's does, but still the sales of their house is actually going down. Now the question that comes down to them is, why is it going down? So what they do is they do a very deep dive analysis, and they see that their delivery time on an average is higher than that of Domino's. Now the question that comes out over here is that, is this difference a statistically significant difference or not? See, for example, for x1, right, the mean time that we require is mu1. Say which is, I'd not say mu1. Mu1 would be a wrong representation to make. Okay, so over here, x1 bar over here is something like this. So say x1 bar, I see that the average delivery time is 8 minutes for Pizza Hut. And for x2, which is the second group, right, or that is Domino's, the average delivery time, or the average time, the average turnaround time for Domino's is 7 minutes 20 seconds. So the question that comes out to our mind is that is it that this is a very significant difference? So is a difference of 8 minutes and 7.2 minutes very different? So is this difference in the average delivery time and the average turnaround time, is this a statistically significant difference? So is this statistically significant difference? So is this difference statistically significant? And this is where we get to, this is where we come, right? So this is what we need to understand, right? So this is what is the statistical significance. So now what I need to investigate is that is this difference statistically significant or not? So the question that now comes up is that how do I identify or how do I distinguish the statistical significance? So over here, yes, we'll again conduct a test. So what is the first question before we conduct the test is that, like, what is the test hypothesis? So over here, the test hypothesis is 80, 0 versus the alternate hypothesis. Right. So over here, what we are trying to do is, so this is what the the mean difference test hypothesis is, that there exists a significant difference in the mean versus there does not exist a significant difference in the mean. So H naught is mu one minus mu two equal to 0 versus alternate hypothesis mu one minus mu two is not equal to 0. Right? So this is what the overall idea is. Now, after this, the next question that we need to understand is that how is it that we would do this? So, what would be the test statistic be like? What is it all about, and so on. So obviously we do not have access to the population mean, as we have also already discussed, right? So what we use, we have the sample mean, and from the sample mean we know that the sample mean is an unbiased estimator of population mean. So if I say that okay, there is the sampling distribution. So how does the sampling distribution work? Sampling distribution for sample 1 is x1 bar follows normal distribution with the mean mu 1 and variance sigma 1 square by n. The next part is x2 bar follows a normal distribution, mean mu 2 sigma square 2 by n. Right. So these are the two sample means. Now we know that the two sample means are unbiased estimators of population mean. Therefore, another important observation that comes from here is expectation of x1 bar is equal to mu1. Expectation of x2 bar is equal to mu. Right. So this is what the two distributions are. So one is x1 bar, the other is x2 bar. Now from here, what we'll talk about is this part. So from here we compute the test statistic. Now we know what is the general structure of the t-test statistic. So over here we have x1 bar minus x2 bar minus the expectations of this is the value. So this is the difference in the mean minus the expected difference whole divided by the standard error of the difference. The standard error of right. So we do not really require to have an understanding of this formula, but yes, we just have a very quick discussion on how this formula will be. Now, since it is expectation of x1 bar minus x2 bar, right? So therefore we know that this is going to be nothing but the means. So over here, what we'll define over here is as follows: x1 bar minus x2 bar mu1 minus all divided by the standard error, right? This is sigma 1 square by n. Or let's say put it as n1 plus sigma 2 square by right. So over here, our basic assumption is that the two samples are independent of each other. Therefore, there is no as covariation associated with them. So over here, this is how the t statistic would look like. Now, what am I trying to test over here? What I'm trying to test over here is that mu1 minus mu2 equal to 0 versus mu1 minus mu2 not equal to 0. That is, whether the difference between the two mean is statistically significant or not. T is equal to, so I am under null hypothesis, the test statistic value would be x1 bar minus x2 bar, because mu1 minus mu2 is equal to 0 under the null hypothesis. So if I want to test whether the null hypothesis is true or not, therefore I put the value of the null hypothesis, right? And most of these testing is done under the assumption of null hypothesis. So after this, so this is how the test statistic looks by end. So this is what the test statistic is. Now, so this is the test statistic under H0. So what we generally do is we try to find the value of the test statistic under H0. Right. So once we have evaluated the statistic value under H0, the next thing that we do over here is we try to develop. So the next thing is we have the testing rule over here. So what is our test rule? That if p is less than alpha, then H0 is rejected at alpha level of significance. If p is less than alpha, so if the p value is less than the alpha value, then this is rejected at, so H naught is rejected. Right. So over here what we have is that H0 is rejected at alpha level of significance. So this is precisely what the t statistic is all about. I mean, the mean difference test is all about. But when we have done this particular test, our assumption, so we have operated under the assumption that these two groups are independent groups. That's the basic discussion. That's the basic description. Now, so this is how the mean difference test is done. Now, the next question that evolves from here are the following. Number one, how do we know that? So, what are the different types of mean difference tests? So over here we have done the we have worked under the assumption that this is something that the two samples are independent. So basically, what are the different kinds of mean difference tests that can happen? What are the different ways of performing these mean difference tests? So that is something that we need to talk about, right? So before I move into that, just tell me whether this part is clear or not. So have you got this part? Great, wonderful. So from here, the next part of statistic that we need to understand is that. So to talk about from here, so what are the different ways? What are the different possibilities of performing mean difference tests? What are the different ways? What are the different mean difference tests? So talking about the mean difference tests over here. Okay. So talking about the different kind of mean difference tests.
Hello?
Yeah, okay, tell me.
Yes, I want to know how much more stats is left, how many class of stats are left?
Stats today is what? Tuesday, right? So stats will get over by Thursday, this Thursday. So after that, we'll start with the core model side of things.
Okay, and what about SAS?
So as we start with the modeling thing, right? So as we go about,
Mhm.
I'll just for the first 3 4 classes, I'll give you I'll walk you through SAS first, so the basic functions, and then as we work with the codes, we'll keep on explaining how I will keep on explaining how one particular function is used for one particular step. So that way you will also get an understanding of SAS, as well as you will also get an understanding of where it is actually used.
Okay.
So because
Because I'll have to get that installed, right?
yeah, so when I start off SAS, I'll get that installed. Don't worry, I do. So you have downloaded that those files, right? I had shared that
Yes,
link.
yes. Yes, yes.
Also, TeamViewer.
Yes, that also I have had.
That also great, 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 perfect. So Harpreet, just give me a reminder on Friday, right? I'll get that installed over Saturday and Sunday because I'm in the middle of so many things. I generally tend to forget. Just give me a reminder. Okay. So over here, the next part that we have is the mean difference. Talking about the mean difference tests. So there are a lot of mean difference tests. Like there are two broad kind of mean difference tests that we have. First is for mean difference test between two groups, and the other is more than two groups. Two groups, and this is more than two groups. Right. So this is two groups and the other is more than two groups. So having said that, so when we have mean difference, when we are trying to do the mean difference test, so up to two groups, we use the t-test. And if we are doing it for more than two groups, we use the ANOVA. So for up to two groups of mean difference test, for two groups, for when we are conducting the mean difference test between two different groups, That is where we use the t-test. And over here on the other hand, what we have is, so if there is more than two groups, what we have is, so what we have is, so over here when we are talking about this, so there are these two groups and more than two groups. So more than two groups we have the ANOVA, right? ANOVA stands for analysis of variance. So if there are more than two groups of values, what we'll do is we'll walk through all the, so we compare the variations across all, and then from there we start off working. Right. So over here, what we get to see is that there is this test. Now, from this, now within these two groups, there are two possibilities. One is the two groups are two independent groups. And the other that we have over here is the dependent. Right. So one is an independent group, right? So the mean difference test is between two independent groups, and the other is the mean difference test between two dependent groups. So there are two types of mean difference test for two groups. One is an independent sample t-test, and the other is a dependent sample t-test. So these are the two different types of things that are there. Now from here, what we have is ANOVA, which is the analysis of variance. So when I talk about the analysis of variance, what I mean is that I'll be comparing it to the variation across multiple groups, and I'll try to identify whether there is a difference in the mean or not. So we'll come down to that test sometimes later, right? So the ANOVA test is a classic example of the test that we generally look into for ANOVA is the if test. So what we perform in ANOVA is called an if test, right? And if test is a very famous variation test. So if test is a very famous variance test. You compare the variance and I try to identify the significance of the mean. Okay. So the next question that we have over here is that, so we have seen over here how the independent sample t-test is done. So the question that comes out to us over here is that where does this, or how do I apply this concept of independent sample t-test in order to in the risk domain. So suppose if I have to develop a risk model, right? Then how do I identify, or in developing a risk model, where does the mean difference test play a role, right? So in this case, what we generally get to see is the following. Let's say, for example, I have identified two segments, right, at acquisition. So what I'm doing is I'm trying to acquire borrowers on my credit card portfolio, and I have identified that there are two segments. So one segment is that of the relationship borrowers, and the second is the new to bank borrowers. So the borrowers who do not have a proper credit history with the bank, and they do not maintain the necessary relationship balance, but they are just applying for a credit card. On the other hand, what we get to see is that there is an independent. So over here, well, what the bank creates a segment over here, right? Okay. So what the bank does is the bank is acquiring borrowers on the books of its for its credit cards, and there are two different groups of borrowers. So one group of borrower is the relationship borrowers. So these are the borrowers who maintain the relationship balance with the bank. And the other that I have over here is the non-relationship borrowers. And both of them are applying for credit cards. Now, what the bank does is the bank identifies that the relationship borrower is a low risk borrower. And the other hand, what we have is the high risk borrower. So, over here, when we have the relationship borrower and the non relationship borrower, the question is how do I identify that these two can be possible segments? If I need to identify these two as possible segments, so then the first thing that I need to do over here is I need to assess that they differ significantly in terms of their average bad rates. So that there is a significant difference in terms of the bad rates. So over here, what we want to try out over here is that whether there is a significant difference in the bad rates. And to do this and to identify that, what the method that we can use over here is the mean difference test for two independent samples. So basically, one application of the mean difference test is in in order to understand, or is in creating segments in order to assess the stability of a segment created. So one important application of the mean difference test is in the stability, to assess the stability of segment created. The stability of segments, right? So this is one very important area where mean difference test is. Now, if there are many segments, say in my data, instead of just two segments, I have four segments. So then there are multiple groups, and to test the stability of the segments and in such a situation, we use ANOVA instead of the mean difference. Right? So is the application of the mean difference test clear to you now? In risk, what is the area and where do we use this? Great. Now coming to the second part, that is the dependent sample t-test. So the dependent sample t-test, nothing much changes. It is just that the nature of the sample changes. So a dependent sample t-test follows exactly the same way. Right? So, however, uh, there is a very important difference that is observed between independent and dependent sample t-test. So in the dependent sample t-test, you must always have the same number of observations because the two samples created are on a fixed number of observations with a pre and a post impact kind of an analysis. Say, for example, a particular credit limit increase strategy has been taken up, right? Or say a particular risk downturn combat strategy has been taken up and it has been targeted that the credit card portfolio needs to be made or the riskiness in the credit card portfolio needs to be largely reduced, right? So over here what we'll do is, okay. So what I want to know is that there has been a downturn combat strategy which has been taken by the bank, and the bank wants to know that has that strategy been effective. So what we do is we take up a population, but a subset of the population, and once we have taken that subset of the population, what we do is we record the overall bad rate in that population after before the treatment has been given, right? Then what we do is we apply the treatment and we keep them in performance for a given period of time. After we have observed them for a sufficient span of time, then we look into their bad rate distribution again. So basically, before the treatment is a group, and after the treatment is another group, and both these group will have the same number of observation because it was a ex post ex ante kind of an analysis that we had done. So once a treatment has been applied, what is the impact of that treatment? Right. So then we try to compare the two groups for the difference in the bad rates, and we try to check whether the decrease in the bad rate that we can observe after the treatment, whether that is significant or not. So that is a part where the mean difference test comes into play. Clear? Great. So this is the part where we get to see this. What should I say? This is the part where we get to see our application of the test. So basically, in assessing the effectiveness of strategies in order to assess the distinction and the overall bad rates, etc., we use this particular approach of mean difference tests. Right? Now, the next part that we need to talk about over here is ANOVA. So over here we have been focusing on two groups of values, but but there can be more than two groups, and that is where the role of ANOVA or analysis of variance comes in. Right? So we'll start ANOVA afresh tomorrow. Within ANOVA, we have two important classifications. One is a one-way ANOVA and the other is a two-way ANOVA. So we'll complete ANOVA tomorrow. And then there are a few basic tests like a chi-square test and all. So I'll talk about that on Thursday. With this, we complete our basic introduction to statistics. So as we move forward after that, we will keep on taking up the advanced statistical concepts one by one. And that will be as a part of the model development exercise that we will go through and so on.
Okay.
Right,
Okay.
good.
So can you please forward me the recordings also so that before starting with the model development, I can just go through these again?
Sure, sure. I'll do it. I'll do it today.